Hello everyone. Welcome back to the channel. Today we are going to understand an extremely important topic in transformer operation, voltage regulation of a transformer. This topic is very important for students preparing for exams, as well as for engineers working in power systems and industries. In this video, we will understand the concept step by step, using simple language, clear explanation, and easy to understand formulae. So let us begin. First, let us understand what voltage regulation actually means. When a transformer is operating without any load, the secondary voltage is at its maximum value. At this condition, no current flows through the secondary winding. Now when a load is connected, current starts flowing through the windings, and because of this, the output voltage reduces slightly. This change in secondary voltage between no load and full load is called voltage regulation. In simple words, voltage regulation tells us how much the output voltage of a transformer drops when load is applied. Now let us look at the standard formula for voltage regulation. Voltage regulation is equal to no load secondary voltage minus full load secondary voltage divided by full load secondary voltage and multiplied by 100. This formula helps engineers express voltage regulation as a percentage. If this percentage value is small, the transformer performance is considered good. If this percentage value is large, the transformer performance is considered poor. Now the next important question is, why does this voltage drop happen? To understand this, we need to look inside the transformer. Inside every transformer, there are primary and secondary windings. These windings have resistance, and they also have leakage reactance. When current flows through winding resistance, a voltage drop occurs. This drop is proportional to current multiplied by resistance. Similarly, leakage flux inside the transformer produces reactance, which causes another voltage drop. This drop is proportional to current multiplied by reactance. So the total voltage drop inside the transformer is the sum of resistive drop and reactive drop. In simple terms, total voltage drop is equal to current times resistance plus current times reactance. As load increases, current increases, and both these voltage drops increase. That is why output voltage decreases under load. Now let us understand how power factor affects voltage regulation. Voltage regulation does not remain the same for all loads. It depends strongly on the power factor of the connected load. Let us first consider a lagging power factor load. Lagging power factor loads include motors, pumps, fans, and compressors. In this case, the reactive component of voltage drop adds to the resistive drop. As a result, the voltage drop becomes higher and voltage regulation increases. That is why in industrial systems, starting large motors often causes noticeable voltage dip. Now let us consider a unity power factor load. In this case, the voltage drop depends mainly on resistance. Voltage regulation is moderate and voltage drop is not very high. Now let us consider a leading power factor load. Leading power factor loads include capacitive systems. In this case, the reactive voltage drop opposes the resistive voltage drop. Because of this, the total voltage drop reduces. In some cases, the output voltage may even increase slightly when load is applied. This condition is called negative voltage regulation. Now let us understand voltage regulation using a practical example. Suppose a transformer gives 440 volts at no load. When full load is connected, the voltage reduces to 420 volts. The voltage drop is 20 volts. Now applying the voltage regulation formula. No load voltage minus full load voltage divided by full load voltage multiplied by 100. This gives a voltage regulation value of around 5%. This value is acceptable for many distribution transformers. Now let us understand why voltage regulation is so important. Good voltage regulation ensures stable voltage supply. Stable voltage helps motors operate efficiently. It prevents excessive heating, and it improves equipment life. Poor voltage regulation can cause many problems. Motors may draw higher current, torque may reduce, insulation may deteriorate, lights may flicker, and electronic equipment may fail. That is why power utilities and industries specify voltage regulation limits. Now let us compare ideal and practical transformers. An ideal transformer has zero resistance, zero leakage reactance, and zero voltage drop. So voltage regulation in an ideal transformer is zero. But in real life, every transformer has resistance and reactance. So voltage regulation is always present. The goal of transformer design is to minimize voltage regulation as much as possible. Now let us see how engineers reduce voltage regulation. They use low-resistance copper windings. They optimize winding layout to reduce leakage flux. They improve core and insulation design. They use tap changers to control output voltage. In large power transformers, on load tap, changers play a major role. Tap changers adjust the turns ratio so that voltage remains within limits even when load changes. Now let us clear one very common confusion. Voltage regulation and efficiency are not the same. Efficiency tells us how much input power is converted into output power. Voltage regulation tells us how stable the output voltage is under changing load. A transformer can have high efficiency but still have poor voltage regulation. So both parameters must be considered separately. Now let us quickly revise what we have learned. Voltage regulation is the change in secondary voltage from no load to full load. It is expressed as a percentage. It depends on current resistance reactance and power factor. Lower voltage regulation means better transformer performance. And voltage regulation is critical for power quality and system reliability. Understanding voltage regulation helps engineers design better transformers, operate power systems safely, and deliver stable electricity to consumers. That brings us to the end of this detailed explanation. If you found this video useful, please like and share it. Subscribe to the channel for more easy and practical engineering concepts. Thank you for watching. See you in the next video.